Okay, continuing on with our practice exam here for second exam of Chem 151. Looking at problem number 4, we've got sample of a gas, we're given the mass, we're told the volume, the temperature, and the pressure, okay, 3 variables from the ideal gas law. We want to calculate the molar mass. So this is a problem where there's multiple routes you could take to solve the problem. For all of them, you do need to recognize that molar mass would be mass per quantity, grams per mole of the material, right? So you really have to know that, or you don't really have anywhere to go. You'd be dead in the water. But from there, you could rearrange P equals nRT to get an equation that incorporates molar mass. You could just work through your units, set them up in a proper way so that everything cancels out except grams per mole. Or in this case, and the way I would probably approach this problem personally, you've already got the mass of the sample. You can use the rest of the information to figure out the moles, then you just need to put them in the right position. So I'm going to solve the problems that way. But before I do that, let me just go through what you could do with the equation. We know P equals nRT, right? And we also know that if you take the mass of something and you divide by the molar mass, you're going to cancel out moles and be left with you're going to cancel out grams and be left with moles. So we can substitute mass over molar mass for N in the ideal gas law, and we could rearrange that equation to solve for molar mass. So if we multiply both sides by molar mass and then divide both sides by P and V, we get an equation that is pre-arranged to solve for molar mass. Now we have to just plug in mass, R, the temperature, the pressure, and the volume in the right units. So that's one way you could approach this problem as well. I do kind of like this one because I already have the mass, to just take that mass, put it on top of a fraction, figure out how many moles of gas there are, and then plug it in there and solve for the problem. Now, this problem is really set up so there's lots of other things we have to do before we can do our ideal gas law problem to solve for how many moles. So if we start with P equals nRT, we would have to divide both sides by R and T. So N is equal to PV over RT, right? And like we've talked about before, we start with R, 0.0821 liter atmosphere per Kelvin mole. Right? Our other units have to match those, or the units don't cancel out. If you put your pressure in millimeters of mercury, it's not going to cancel with the atmospheres here. You'll still have extraneous units when you get to the end. So for each of the units here, we'll need to make a change before we kind of plug them in there. Or you could kind of cobble all the math together and do the conversions while you're plugging in. That gets a little messy for my taste, right? Yeah, because I'm so organized on the page. Starting with the pressure, our pressure is 886 millimeters of mercury, and 1 atmosphere is equal to 760 millimeters of mercury. That conversion will give us the pressure that we want here. So 886 divided by 760 is, and I'm going to keep at least one extra figure here, 1.166 atmospheres. And again, if you can keep it in your calculator, that's even better. But if you keep at least one extra, that should minimize any changes due to rounding off that might pop up in your problem. The second thing there, P times V on top there, the volume. The volume is in milliliters. That should be liters to cancel with the units of R, but since there's 1,000 milliliters in a liter, I'm just going to move the decimal 3 places to 0.224 liters. Right now, if you want to do that as a step where you put in 1 in 1,000, up to you, right? As long as you're getting the right answer, that's what's important. I think we have had a lot of experience with that one, so you might be a little more comfortable with that one. And then the temperature on the bottom has to be in Kelvin. The temperature is 55 Celsius, so if we add 273, we get 328 kelvins for our temperature. And that, like I said, will tell us how many moles of gas are in the sample. So 1.166 times 0.224 divided by 0.0821, and also on the bottom, so divided by 328. That is 9.699 times 10 to the minus third moles of gas. Now again, we're not quite done because we were looking for molar mass in the problem, and I did that up there at the top, but let me bring it down here. Molar mass would be the mass of the gas sample divided by how many moles of the gas sample there are. That will give us the correct units for molar mass. So 0.0388, and then I'm going to pull up the previous answer. Whoops, I should divide before I pull up the previous answer. Divided by previous answer, 4. Right? And to 3 significant figures, right? Looking back, everything is 3 significant figures. Our temperature is 3 when it's converted to Kelvin. That should also be 3 significant figures. So 4.00 grams per mole is our answer there for the molar mass of this gas. Now, there's a bonus question down here, and we talked about the kinetic molecular theory and some of the equations that stem from that, and I described that as something you should understand relationships even if we're not doing any calculations. Actually, this doesn't quite relate to kinetic molecular theory. Maybe I should read the bonus question before I start extemporaneously describing it. Is the gas denser than air? This would actually relate more to the equation that I derived over here. If we want to think about gas density, that is mass per unit volume. So if I kind of ignore the molar mass version here, I could take that previous equation and rearrange that to solve for the density, right? Since density is mass over volume. So if I divide both sides by volume on the right here, I could get mass over volume, and then all the other pieces would have to move to the left. So I'd multiply by molar mass. Whoops, I had volume I moved, just molar mass times P, and then I divide both by RT. That would give me the molar mass times the pressure divided by R, and the temperature is equal to mass over volume, which is density. Right, mass per unit volume. So in this case, the molar mass of whatever gas we're describing is directly proportional to the density of that gas. Higher molar mass, higher density. Lower molar mass, lower density. Air is made up of oxygen and nitrogen. The molar mass of oxygen is 32 grams per mole. Molar mass of nitrogen is 28 grams per mole. So air we could think of as somewhere in between 28 and 32, and that's actually quite a bit more nitrogen than oxygen, so it's probably like 29 grams per mole. But either way, that's a lot more than 4. 4 is actually helium, which is much less dense than air. That's why helium balloons float. That's why you can fill a blimp with helium and get it to float through the air. So is the gas denser than air? The answer is no. Right? In fact, it's less dense than air. Right? And I gave a lot more description there than is required for the bonus question, right? You're really answering yes or no. But the rationale does come from this equation back here. Okay, carried on for a bit on that one, so we'll make that a standalone video, and we'll come back for problem 5 in the next video.